Welcome to all. Myself, Dr. Santhosh Singh, working as an Associate Professor in Department of Physics, Institute of Aeronautical Engineering. Today I am going to discuss about acceptance angle of optical fiber or fiber optics. So I already discussed about some basic feature of optical fiber cable or fiber optics. So today I will discuss something more about acceptance angle and how the wave will propagated, why it will not last through the optical fiber cable, all these things. So the one main thing is for launching the wave so that it can propagate through the optical fiber cable without any disturbance or without any losses. So this thing means acceptance angle is a very important things for governing the launching angle so that your wave will be not lost or not gone for any attenuation. So what is the acceptance angle? So it is defined as the maximum angle of incidence at the end face of the optical fiber for which the ray can be propagated through the core material. It is also called as acceptance cone half angle. So basically, see, this is your optical fiber cable or optical fiber, and it consists mainly three parts. The center part is core. The outer part of the center region is known as cladding, and this outermost part will provide some mechanical strength for these two assemblies. So it is known as buffer jacket or some time called coating, mechanical coating, so that your main part, core and cladding region will be safe. So see, this core region is considered here in yellow color, and this cladding region itself same color, green. Okay. Now I already told that your rays will always propagate through this core region by several multiple internal reflection. What is internal reflection or total internal reflection? I already discussed in my last video lecture. So why if you launch the rays at any angle or at any incidence angle, will it go for total internal reflection? No, there are particular angle. Within that angle, if you launch your ray, it will go for total internal reflection, and your data will be, your information will be safe. Okay. Why? Because due to total internal reflection, the rays will not come out from optical fiber region. It will not come out. It will always travel through the core region. Okay. So there are some particular angle. If you launch your ray at that particular angle or within that region or limit, then only your rays will go for total internal reflection phenomena, and whatever the data or information will contain along with that ray will be safe. Okay. So suppose here in this figure only two surfaces of optical fiber cable is visible. One is this, suppose. Second one is this. But your optical fiber cable is a kind of cylindrical waveguide. So totally there are n surfaces, not two surfaces. For one, but here we, due to some constraint, we cannot show here exactly. This is basically two-dimensional figure. And actually, your optical fiber cable is in three-dimensional geometry. So there are, you can see there are n number of core cladding interface surface. But here you can say 1 and 2. In this figure, you can say only two surface, core cladding interface surface. Okay. So for example, we will discuss for these two surfaces, and we will extend our philosophy for entire surfaces. entire core cladding interface surface. So let's consider this is for this first surface. This is core region. This is cladding region. And if your launching rays is strike over core and cladding region beyond the critical angle or minimum at critical angle, it will go for total internal reflection. That is the main criteria for getting the communication or for sending the data or information through the optical fiber cable. So suppose this is the ray and it is exactly, this ray is actually launched in air. Now this air have different refractive index. Now it is entering in core region at this point. So obviously it will try to move towards the normal at this point due to reflection, because ray is coming from air, means rare medium, to denser medium. So it will little bit deviated towards the normal. This is the normal at this point. So that's why you are seeing some not exact straight line. It is going like that. Now this is the core cladding interface, and if this angle phi is at equal to the critical angle, then what happens? This ray will reflected back in the same medium. Okay. So this angle is actually important. Okay. It for this launch inside the optical fiber network, the ray is launching at core and cladding interface at exactly critical angle. Okay. So this launch is important in the air, or this angle is also important. If you little bit increase the angle, what happen? It will bends more towards the normal, and now it will hit somewhere here. Let's suppose this is the ray. Now this is launching at this angle. Okay. Now for this launch, let's suppose this is making the critical angle launch at core cladding interface. Okay. Now if you are launching another ray greater than this angle here, so what happens? It will try to go like that, but actually it will little bit bend, and now this angle is less than critical angle. Okay, it will become less than critical angle, so it will not go for this angle. Let's suppose this is phi dash, and this phi dash will be less than phi. This phi is equal to theta c, critical angle, so it will not go for total internal reflection. Why? Because it will not go for total internal reflection, because this incident ray is not launching at critical angle. It is less than the critical angle. If it will launch beyond the critical angle, or at least at critical angle, it will go for total internal reflection. So this is one ray for this surface. Now similar case you can imagine for this second surface. So this is a kind of triangle you can imagine for two surfaces. Now rotate this triangle for covering the entire surfaces, entire core cladding interface surfaces. What you will get? You will get a kind of cone. You can imagine a kind of cone. Okay. So that cone is known as acceptance cone. Why acceptance word is used here? Why? Because inside this cone, whatever the rays will launch inside this cone, they will go for total internal reflection. Okay. Others ray will fall over the core cladding interface less than the critical angle. Whatever the ray will be inside, whatever the ray will be inside this cone, imagine one cone by rotating this triangle. So whatever the ray will be inside this cone will go for total internal reflection. Why? Because all the ray will hit the core cladding interface beyond the critical angle or at least the critical angle, so that they can go for total phenomena of total internal reflection. Okay. So that is the working principle of optical fiber cable. If any rays will launch beyond or at least the critical angle, they will go for total internal reflection. And whatever the data or information contained with that ray will be safe. Okay. So, hope it is clear what is acceptance cone. Now, every cone, let's suppose this is the cone. Okay. This cone have a height h and base radius r. So there are one vertex angle for associated with every cone, and let's suppose this angle is theta. So half of this angle, theta by 2, okay, you can imagine easily. So here you can also imagine one vertex angle by visualizing this cone. So half of this angle is known as, let's suppose this vertex angle is theta. So half of this theta, theta by 2, means what? This angle, let's suppose phi, is known as acceptance angle. So acceptance angle is nothing but it is associated with acceptance cone, and whatever the vertex angle, half of that angle is known as acceptance angle. Okay. Why it is important? What are the importance of acceptance angle and acceptance cone? If any rays will launch within inside of acceptance cone, that rays will go for total internal reflection, and whatever the data or information contained with that ray will be saved. Okay. So same thing is written here. The cone obtained by rotating a ray at the end face of an optical fiber around the fiber axis with the acceptance angle is known as acceptance cone. Light launched at the fiber end within this acceptance cone alone will be accepted. Within this cone, only it is accepted or acceptable. Other rays will go outside. There are the chances they will come out from the optical fiber. So there is some safety issue with your information or data which are associated with this light ray. Okay. So light launched at the fiber end within this acceptance cone alone will be accepted and propagated to the other end of the fiber by total internal reflection. Larger acceptance angle make launching easier. If this acceptance angle is having larger value, means there are chance you can launch the ray here. Okay. If it is very less, so you can launch less number of wave. Okay. So if the acceptance angle is greater, so launching is easier. Now we will derive some expression for acceptance angle. Okay. So actually acceptance angle is associated with acceptance cone. This is your acceptance cone. Now this angle, half of this angle, let's suppose this is theta. So theta by 2, that is this one. So this one is, let's suppose phi. So this phi is your acceptance angle. Okay. So now we will try to derive the expression for this acceptance angle. Here in this figure it is written as theta naught. Okay. So let's suppose in this is your core region, this is cladding region of optical fiber. Now you are launching one rays from the air. Now this ray is hitting the optical fiber cable at point O. Now this ray is coming from rarer medium because outside is air and entering in little bit denser medium because this core is made with the help of some glass or kind of dielectric material. So these dielectric material obviously have some higher refractive index than air. So let's suppose this outer refractive index is N1 or N0. This core have refractive index N1 and this cladding have refractive index N2. Okay. So for light ray propagate through the optical fiber by total internal reflection, they must incident on the fiber core within the angle theta naught. Okay, called the acceptance angle. Now apply the Snell's law at point B. At point B, apply the Snell's law here. Now this, anyhow, this become, let's suppose after refraction this angle is theta 1, then this alternate angle also become theta 1. So this one will be 90 minus theta 1. Now at point B means here they are exactly parallel to the core cladding interface surface. So means this angle is critical angle. Okay. Means you are launching exactly at, you are launching the ray exactly at the critical angle. So apply the Snell's law at point B. So what is Snell's law? Refractive index of this medium N1, then sine of this incidence angle 90 minus theta 1 is equal to N2 refractive index of this medium, then sine of this angle of reflection, and here angle of reflection is 90. So 90 you can write. So sine 90 minus theta you can write cos N1 cos theta 1. N1 cos theta 1 is equal to N2 because sine 90 is 1. So N1 cos theta 1 become N2. Now cos theta 1 is, you can write N2 upon N1. So by trigonometry sine theta 1 minus cos square theta 1 power half. So cos theta 1 is N2 by N1. So in the place of cos square theta 1, you can write N2 square upon N1 square. So sin theta 1 is equal to 1 minus N2 square minus N1 square whole to power half. Now apply Snell's law at point O, this point. Same Snell's law. So here, let's suppose the outer refractive index is N0. So how you can apply the Snell's law? N0. This N0 is refractive index of air. Its general value is 1. Sine launching angle sine theta naught. Sine theta naught. This expression you have to calculate the acceptance angle sine theta naught. Okay. So N0 sine theta naught is N1, then angle of reflection sine theta 1. Okay. So N0 sine theta naught is N1 sine theta 1, or sine theta naught is equal to, you can write N1 upon N0 upon sine theta 1. Okay. Now substituting the equation 1 in equation 2. This is equation 2. This is your equation 1 where sine theta 1 value you already have. So sine theta 1 value is 1 minus N2 square upon N1 square, N2 square upon N1 square whole to the power 1 by half. You can put here. So you will get sine theta naught here. Sine theta, this value, sine theta 1. You can put here. So what you will get, sine theta naught is equal to n1 upon n naught by 1 minus n2 square upon n1 square whole to the power half. Once you simplified it, you will get n1 square minus n2 square, n1 square minus n2 square upon n1 square, and this is inside the under root. So once it will come out, it will cancel n1 by n naught. Okay. Now I already told n naught value is 1. So sine theta naught, sine of acceptance angle is what? n1 square minus n2 square. So theta naught, actually acceptance angle is sine square. This is not by, this is sine inverse n1 square minus n2 square. Theta naught is equal to sine inverse n1 square minus n2 square. This equation is known as equation for acceptance angle. Okay. So light gathering capacity, that if you able to understand now what is acceptance angle and acceptance cone, so we will discuss about numerical aperture. Numerical aperture is a very fundamental property associated with any optical fiber, and its literal meaning is light gathering capacity, which how much light the optical fiber cable can allow by themselves without any disturbance. Means how much light rays any optical fiber cable can allow, so that light rays can travels from one end to another end without getting any disturbance and without lost their characteristics or lost their data or information. So that thing is associated with numerical aperture. So numerical aperture is gathering capacity of any optical fiber cable. So that thing is associated with sine of acceptance angle, theta naught, is known as numerical aperture. Okay. So theta naught itself known as acceptance angle, and once you associate sine with this theta naught, it is known as numerical aperture. So sine theta naught, just now you derived n1 square minus n2 square power 1 by 2 under root. So this thing is also known as numerical aperture. Okay. So once you are able to calculate the acceptance angle and able to understand the acceptance cones, you can clearly tell about the numerical aperture, light gathering capacity of any optical fiber cable. So that's why this acceptance cone and acceptance angle is very, very important. What is the capacity of any optical fiber cable? So that any rays or number of rays can travel through that optical fiber cable without any disturbance is associated with numerical aperture, and numerical aperture is nothing but that gathering capacity, and its value is sine of acceptance angle. Okay. So NA, in short term, NA numerical aperture is nothing but N1 square minus N2 square. What is N1? Core refractive index of core. And what is N2? Refractive index of cladding. So light gathering capacity is proportional to the acceptance angle, obviously. NA numerical aperture is sine of theta naught. So NA is directly proportional to theta naught. So numerical aperture can be represented by sine of the acceptance angle. NA is equal to sine theta naught. So that's all for today's discussion. We will discuss some more thing about numerical aperture in next video lecture. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.